so much to say that I can get through all. So, my name is Tim. I live up in Evanston, and I work for Walmart. They're based in California. I'm here to talk about scaling to meet demand. It's going to be a pretty wide-ranging talk. I don't have nearly the code examples that we saw from people like Jeff, but I'm going to be talking about some of the ways in which we scale to meet the highest level of demand. So a little bit of background here. I'm going to be sharing some of the lessons learned and some of the patterns. I'm not going to be making any news. I'm not going to be announcing too much about the details of what we do specifically. That's sort of not my role to share that. But I want to talk about some of the lessons I've learned over the last 2 years, helping them meet the demand that they have to meet every day. So I have an engineering background, and I got addicted to failure when I was in engineering school, just the study of failure. It's fascinating to me. And so I'm going to emphasize failure a lot, but that's not to say that we fail. Right? But I think that failure is something that, as an industry, programmers don't think about failure enough. We focus on the requirements and stories, we build our systems to work, and then we ship them to production. And we very frequently only learn about failures after things are shipped to production. When you're at scale, you just can't afford to do that. So to me, what does scale mean? I think a lot of people mistake performance for scale. Right? If you're going to scale something, then you got to do pages to render quickly, you've got to be able to handle load, you've got to be able to test your system under load. I think that's only one factor of scale. Under high load, you also want to be able to perform at capacity. Right? You want to be able to satisfy your promise to the customer when you're experiencing the highest load possible. And the other thing is failure. You have to have a culture of failure. Right? Everyone has to be comfortable with failure, have to be comfortable talking about failure. You have to find the root cause for every failure and document it. So one of the books that I was introduced to in college was To Engineer is Human. And it's a book that programmers don't read, right? We get CS degrees, some of us major in comparative religion or whatever it is. We're a very sort of free-form industry. You don't go through a very rigorous engineering education like you would if you were, say, building a bridge or designing a space shuttle. But this book is focused on just that. It's focused on mechanical engineering failures, civil engineering failures. If you're not into it, it might seem a little dry. But if you start thinking about how engineering uses failure to progress, it's fascinating. It's also addictive. And you also won't be able to stop thinking about it. Every time I get in an airplane, I think about the DC-10 crash. That doesn't make for a very comfortable ride. But the planes that we ride on, the bridges that we walk on every day, they're safe because of failure, right? So one organization, these were the heroes that I grew up with. This is Gene Kranz. He's the mission control for the Apollo missions, right? All of these people, you can tell it's a different time entirely, right? All these people are sitting in front of a TV screen watching humans on the moon, right? And that happened in like a decade, right? The president announced it as a goal, and NASA sort of achieved this level of success because of failure. We had all these Saturn launches, right? We launched all these Saturn rockets into space. Not one of these rockets blew up during a mission, right? Which I know it's sort of a strange thing to think about, but that's the kind of thing you think about when you're focused on failure. That's not to say they didn't have their share of problems, right? This is from the last decade, this is from the 60s. Every time something went wrong in the Apollo mission, they documented it. One of the leading software engineers for the Apollo mission, she built in contingencies to all of the software control that was on the Apollo capsules. They were able to patch the software when it was in flight. They were able to dial switches when they were in transit to the moon, right? So these are all things that are interesting, but we don't build rockets. That's not why you're here today, right? We build software systems, a lot of us build websites. Although at times, it really actually does feel like we work on systems that are more complex than the Apollo program, if you want to measure that by the number of meetings we have to attend. So I want to just bring it back to software. We are focused as an industry I think on this. This is something that we all focus on. I think everybody who's invested in software design, in the back of their mind thinks, if I was going to start a startup, what would I do it on? I would use cloud infrastructure. I'd probably do it in a mixture of languages. Maybe you're a Ruby on Rails person. Maybe you like Python. Maybe you're a .NET person, right? But this is literally like if someone came to you and said, I want to create a system. I want it to scale. I want to do a startup. This is what you do. Simple technology, probably make it a polyglot platform. You would use a relational database, but you'd probably also have a NoSQL store or something like a key value store to back it up. You would use a CDN. These days, more and more application logic is shifting to client-side systems like Angular and React or Backbone. You would absolutely want to deliver your client there, and you have integration with the usual suspects. If I were building a startup from scratch, I needed to sell things, I'd probably use these services. For the build and deploy systems, in a startup, you have a single team, right? You usually don't have a build and deploy team at your startup. You have maybe one or two people who are focused on builds and deploys. You have a single deployment. This is something that you'll hear said a lot at a startup, deploy version 2 of the entire company to production. Most things these days are cloud-based. Most everything is automated. Alerting and monitoring, you can use a bunch of third-party systems like Splunk and log entries. And the volumes that you have to worry about are gigabytes of logs per day, if that, maybe hundreds of megabytes. And these are systems that everybody should be familiar with. We could have a competition and see how quickly people can come up with this. From zero to a fully supportable startup model probably would take me about a week. I've got kids and a life to live. It probably takes some other people about a day to get them done, a couple hours. There's cookbooks out there. Now that's the startup architecture. The scaled architecture, that's not sure. The scaled architecture is something entirely different, right? So this is a company that's operating at scale. And if I were to draw the real network diagram that shows you all of the different components that were involved in a company like Facebook or a company like Google, it would take up this entire wall, right? And if it were drawn to scale, you'd see data centers all over the world. You'd see multiple CDNs. You'd see instances where this is, say, a front-end layer that serves the website. Each of these blue boxes is maybe a team of 20 to 50. Each of these, the larger boxes is a department. There's a department that's responsible for services. Maybe there's multiple levels of services, right? Things that you heard about in the last presentation, patterns for rendering a website. You want to have synchronous service calls or asynchronous service calls. There's a mixture of technologies. At a very large technology company, you're using a mixture of Node.js, Java, you're using some Clojure, you're using some .NET, basically all the languages. You're interacting with about as many databases as you can imagine. Maybe the main ones are Oracle. You've got some MySQL in there, just a few Postgres. For build and deploy, you're talking about a build and deploy system that has to support hundreds of teams. You might have a standard, which is used by 95% of those teams. You're always going to have exceptions, right? You'll maybe standardize on Maven, but there'll be some teams that use Gradle. You'll have many deployments a day to cloud infrastructure. So at Walmart, we're one of the biggest installations of OpenStack out there. So we use OpenStack. We have tenants in the cloud, multiple data centers, multiple clouds per data center. When people do deployments, we're talking about hundreds of thousands of machines at once. So it's a very different model between that startup architecture and that scaled architecture. And the challenge and the promise is how do you do this, but still preserve this ability for teams to move independently, the ability for teams to deliver in sort of an agile process. I'm going to talk about in this presentation how do we manage some of those differences and how do we make sure that we can achieve scale. Right? We also have stuff like common configuration libraries, common logging libraries, common automation frameworks. In an environment like this, it's not so much you ask every team end-to-end to deploy the latest version of the site, right? the question that you ask most often is, what's the conference bridge for the release process? So it's a whole different way of thinking. But at the same time, we have to find a way to scale from that startup architecture to the scale architecture. So there's a couple differences. In a startup architecture, there's really an emphasis on getting it done, right? Can move quickly. There are very few obstacles to progress. You don't have to have too many meetings at a startup to decide what your release process is going to be. It's usually one or two people. They can press a button, get it done. Some risk at a startup is acceptable. Twitter made famous the concept of the fail whale, right? But that's not something that is acceptable when you're running certain kinds of websites. You are your support, and that's the thing that I think most of us don't realize when we make the transition to a scale architecture. We have this image of the developer and DevOps as being this independent island of independence, right? In a scale architecture, you have so many teams that are available to help you. You have network engineering, you have site ops, you have problem management, and all of these teams are there with resources. It's getting people ready for this idea that scale is about people. In a scale architecture, you have an emphasis on stability, right? If you work at a bank, if you work at an insurance company, it's about keeping systems up and running, 4 nines, 5 nines. But there's change control processes. If you work at a large company, there's Sarbanes-Oxley. Every change has to be tracked. It's not a choice. You're risk averse, but then you're also trying to balance this risk averse nature with trying to enable teams to move quickly. You have several support teams. So you think you're going from a Ferrari to an aircraft carrier, but in reality, once it hits you, the magnitude of the challenge and the size of the team, you're actually looking at a system that's more like this. An aircraft carrier doesn't go alone. There's a whole support carrier group around it. If you want to scale this even higher, there's multiple carrier groups. And I hate to use this as an example because it's not the most peaceful example in the world, but when you're working at scale, you've got a fleet, and you have to figure out how to coordinate operations between, components of that fleet. That is to say this: if you go to technology conferences and you want to hear people talk about scale, you want to hear somebody from Facebook or Google talk about scale, we tend to cargo cult scalability. We tend to say, well, what does Netflix use to manage their configuration? If we use Netflix tools, we'll be like Netflix. If we use the tools Google uses, we'll be like Google. Right? In reality, scalability in technology is only one component. The real secret sauce is the number of people involved when you have to scale systems. It's not about you using the right build and deployment tool or you using the right build systems. It really is about getting to the point where you can operate a system that has the right people talking to each other at the right times to guarantee that the right things happen. And, I was going to put a picture of our NOC in here, but then I had second thoughts about that. This is the NOC. I think in Houston has a room that looks a lot like this where I work. So how do you scale? There's a couple of components. I think one is you manage, anticipate, and track failure. And I just can't say this enough. If something breaks, it doesn't matter how tiny it is, you have to track it. You have to figure out why it happened. Who was responsible is something that's important, but you don't want to dwell on blame. The culture of failure is not about finding out who blamed, right? It's about finding out what went wrong. You need to test performance capacity, and this is something that, again, I think people don't think about until something goes into production. You do that way before those bits are going to, that war file or whatever, hits Tom Petty. And then the important things I would emphasize are you want to distribute some responsibility to the team, and this is sort of in line with the movement towards DevOps. Then you also want to communicate. And this is another thing that I think, as programmers, we've got a lot of work to do, right? We tend to just want to write code, throw it over the wall of confusion, if you will, and let the ops deal with it. DevOps is about developers taking more responsibility for how our code executes on production hardware. Again, I'm addicted to failure. I love it. I don't love failure itself, but I like chasing failures. If something goes wrong, this is sort of what I do, right? Every time I open my laptop, I'm sucked into something, and I have to stay with it for like 4 or 5 hours. If there's a little tiny problem, you have to just go through a whole investigative process to figure out what's wrong. And everything, I'm going to talk about 3 things to failure. Everything needs a timeout. Configuration is a whole different ballgame at scale. And then everybody needs to enforce a performance budget. All right, let's talk about timeouts. Timeouts. Who here runs a website that has some concept of maximum acceptable render time? Like, on your site, do you sort of give up after 6 or 7 seconds? Tell people it's too late? Like, if you've used Reddit when it's under load, you'll know that it just says, sorry, it took us too long to render this page. Timeouts are protecting limited resources. And because of the reality that we live in, everything is a limited resource. At scale, you really need to be thinking about your capacity, and then what are you going to do to protect your capacity under scale, right? Timeouts are that. Timeouts protect your capacity. If you've got 1 billion users coming to you trying to buy the same thing at once, you want to make sure, A, that you've tested this to capacity. You make sure you have the capacity. But you also want to make sure that if there's a problem in a system, and problems are unavoidable in complex systems, that you react with intelligently. That's why everything needs to have a timeout. If you were to go to Stadium, Stadium has a built-in capacity. They won't let more people in, more than the fire code allows. That's one concept of a hard limit. But then inside the stadium, if you were going to go buy a beverage, you would look at the line and you'd say, do I want to stay with that? Website users during high-load events don't have the luxury of being able to see how long that line is. And so you want to make sure that you don't let people in if you can't handle it. First, you want to make sure you can handle it. Second, if there's an issue, you want to make sure you can handle it intelligently. At scale, you need to make sure that small problems don't affect the overall system. And that timeouts are not SLAs. We'll talk about that in a second. Different timeouts for different purposes. So we've got 3 types of timeouts. There's a server timeout, application timeouts, and then internal timeouts to services. Servers have timeouts, and one of the things that I've noticed is that people who are new to scale, they don't bother setting them, right? So there's a hard timeout for something like Apache. You can set the maximum amount of time that I'm willing to wait for something to finish. If that doesn't happen, timeout. If you don't set these hard timeouts, these backstops, if you will, computers are great at doing exactly what you ask them to do. And you might have a system that waits for multiple minutes to return a website. Now that's not something that a user is ever going to do. A user is going to wait a couple seconds, and if that, that's why you need to make sure that your timeouts are set on your Apaches, your timeouts are set on your Tomcats. You need to understand with incredible detail how your load balancers work. Right? Load balancers are not just things that network engineers set up for you that'll sit in front of your websites. You need to really understand how the F5s, how the net scaling work. You need to understand how KeepAlive work, HTTP KeepAlive. Critical to performance, right? You're not creating a new connection every time you load a web page. You're creating one connection and you're sending multiple requests over it. That's incredibly useful. But you're also creating a connection that's long-lived. And if you've got 5 or 6 levels, you've got a NetScaler, you've got a CDN, you've got multiple devices in front of an Apache, and then you've got a Tomcat, you've got that connection open. What closes it if there's an idle time? And that's a big question at scale. The answer is usually you want to let your load balancer handle that. Application timeouts. This goes back to the idea that as developers, we focus on the requirement, right? Getting the user to be able to see something on a site. Getting the user to be able to go through a specific transaction. What we need to be thinking about is defensive timeouts inside the request. It's not just good enough for the request to have a timeout. If your request calls out to 3 different services and has to render several different parts of the page, there are different parts of that page that are more critical than others, right? So you should be able to have an internal timeout that says, do I really need to show the sort of extra special badge that I'm trying to put on this one product? If that badge requires a call to a service that's failing, I don't want to stop the whole page from rendering. I just want a timeout for that one service call. The other thing that you want to do is, if you've got a system that's making several service calls, in the context of your overall request budget, you want to have systems that are smart enough to say, I've really only got 2 seconds to render this page to be within spec. It's a second and a half since that timer started, and calling this other service is going to take more than 500 milliseconds. I'm going to skip it, right? So preempt calling back-end services if your performance budget is running out for a particular request. These are the kinds of things you have to do, or else you're just going to have systems that are constantly trying to make calls to services and timing out. One thing I will tell you is that we use a lot of futures. So when you render a page, we create a future to render the page in Java. And that future creates more futures. It's a hierarchy of futures, if you will. So in Java, we say future, render the whole page. Inside of that future, we call a future to render the header. Then we have a future to render the body, and a future to render the footer. Inside of the header, we have a future to call it to services. We have a future to render the nav, a future to render the login information. So if you look at this, this is a dramatically simplified picture of all of our futures. Futures are fire and forget. So in Java, you need to build in some logic to be able to say, I fired this, and I'm only going to give it a second to finish. And then within that second, you need to have other logic here that says, I fired this, I only have a second to run. So these are all the other features I want to run. They have to complete in this set amount of time.
So how do you do, in your example earlier, you're talking about the 1.5 seconds, and then we don't even bother to call it. In this model, you would have already invoked the future for second service.
So I won't go into too much of the details, but for example, I'll say if you get down to here, you know when that future was kicked off. When that future actually starts to execute, you can call back and find out where are you in the overall timeline for the page render, right? And at that point, you can say, I really only have another 600 milliseconds to run this. Based on what my current stats are, I don't think I'm going to be able to get this, so I'll skip it. Or I'll selectively degrade what's on the page based on the performance at that given time. Right? So it's like saying, we're going to render the whole page in a series of features, but within those features, we're going to have some logic that says, is this worth it? If that makes any sense. Does that make sense?
I think so.
Okay. When you have timeouts, which I think are essential for everything, regardless of whether or not your systems are synchronous or asynchronous, you still need to have timeouts. Right? You still need to have some upper limit on what's going to happen. You need to log all of them. Logging is like a whole hour-long conversation, but you need to have, if you have thousands, tens of thousands of servers, you need to have log aggregation. It's a science in and of itself how to do this right. You need to have some systems like Splunk or something like Presto or Hive to be able to query these log timeouts. You need to have a way to report on them in real time so that mission control can see that graph. You need to understand what percentage of users were affected. Hopefully that's a very small number. And you want to make sure that your timeouts don't mask real problems. So you time out because there's an issue with a response time. You time out because there's a problem. You don't time out so that you can ignore what that problem is. So we'll go back to this in a second. So you got this runtime system, you've got timeouts configured, you're protecting your capacity. Let's talk about configuration. So this is a picture of a physical manifestation of configuration for a mission critical system, right? When you're in the air, when you're flying from San Francisco to Chicago, and there's a problem in that flight, something up here beeps, something down here beeps, and there's a switch, right? There are multiple redundant systems in an airplane, but what you don't see, at least very often, is you don't see a pilot saying, oh, let me go in the back, see what's going on with it here, right? You don't see the pilot get up, take a wrench, go to the landing gear, and bang on it, right? Although I was on that flight, it was a small plane, and that was one of the most uncomfortable experiences of my life. what you have all these switches, and switches that can be changed at runtime. And this is what aerospace is used to. If you run a system of satellites, and I've worked with people who do, you can upgrade everything remotely on that satellite. You know, the Mars rover was upgraded remotely. They rebuilt the entire software. It took a day. It's a risky operation. But they could also split switches. Those switches happen to have an 8-minute lag time for when they can figure out if they work. But the point of systems at scale is that you need to think about your system, if it's operating in a really high profile, high scale environment, it needs to be able to be changed at runtime. One second. I wonder how that's going to affect my Apple remote. You need to be able to flip a switch and turn off features. If something happens, so your system is dependent on so many third-party services and so many internal services, which could be third-party services for what it's worth. You need to be able to say, you know, if there's an issue with loading this particular service, let's dial down the rate at which we call it. Or let's turn that service off completely. Let's protect the core customer experience. Let's find a way to grade gracefully. And if you can't do that, switch on and switch off at runtime, you failed. This is something you see in the startup architecture quite a bit, and I've seen it very frequently in certain languages. People just want to bundle properties files with their systems. They want to just put a properties file in the system that points to different service endpoints. They want to put a properties file that talks about queue sizes. And if you do that, you're going to have a hard time. So sometimes people from startups show up and at scale, you need to say, listen, everything's configurable. Everything that's configurable needs to be configurable at runtime, and it can't require a restart. If it's a feature, any kind, it's got to have a switch on it. You've got to be able to turn it on and turn it off. It's also a great way to make releases less risky, right? If your release involves publishing a WAR file to a Tomcat, seeing if it works, that's a failure. Your release has to be publish a version, and then at a later date, let's switch it on. And if it doesn't work, you can switch it off in a second. All of your features should have that toggle. You know, use something like Zookeeper. At the peak of your load, you don't want to have to reboot anything. You don't want to have to restart your Tomcats. You don't even want to have to kill a process running a Node.js app and restart it. Even though many of those things, I mean, restarting a Tomcat can be an expensive ordeal. Restarting a Node.js app can be like the snap of a finger, but it still involves interrupting somebody's request. It involves taking a TCP IP socket down, whatever you want to call it. What you want to do is you want to avoid events that are going to create any blips in your uptime graphs. Changes should be immediate-ish. So that's configuration. I want to talk about the budget. So this is the Senate. This is a quick snapshot of the federal budget. You see there's things we have to spend, things we choose to spend, and there's stuff that's related to federal debt. Now, I'm not talking about government here, but your performance budget is the same. It's not exactly the same. Right? It doesn't require legislation to change your performance budget. But there are things that you have to pay. For example, the speed of light between your customers and your data centers. You're not changing that unless there's something I don't know. There's stuff like the latency of network devices, you know, down to the wire, on a level of the OSI, you know, stuff that I'm not familiar with. That stuff that you're not going to fix. But there's things that are under your control. What's going on here? There are application render times. There's two kinds of performance these days. There's client-side, sort of web-focused performance, which is a science in and of itself. In fact, if you're at a high enough scale, there's a whole different team that's focused on things like how is the DOM being rendered, and you know how is something like Angular or React or Backbone, how are those interacting with called out static assets. There's server-side performance budgets, and there's also performance budgets for back-end services. Everything you call as a service needs to have an SLA, right? And it's a service level agreement. It's a commitment to how quickly it should take to render, say, a page. It's a measurement of how quickly it should take to call out to a service. And all of that stuff needs to be measured, tracked, and constantly accounted for. You should have dashboards that you can look at for your website that measure what are all the various SLAs for all the teams that are contributing to a page rank, right? Are there teams that are out of SLA? Are there teams that are within their SLA? That's stuff that you should be monitoring before you go into production. You should also have a team. This is a cross-domain team, right? This would be a team that involves operations and developers and architects and whoever you want, that has a meeting that talks about what are our current performance budgets? How do we reduce time spent in this phase of page rendering? How do we reduce time spent calling out to services? Is this feature we just added, is it worth it? Right? And that's something, cost-benefit analysis is also something you don't see IT professionals getting into very much. If you create a new feature, let's say to show like a new widget on a page, and that feature adds a second to your page load time, you need to have a statistic that says, if we make users wait another second, it'll affect conversion by this much, it'll affect revenue by this much, right? So having those discussions isn't something that you think of developers having, but we need to be involved in that discussion because we're the ones who have the technical information. That's a pretty important thing to start doing. Simple components to track. Again, there's something like SpeedCurve, which is a service, a third-party service. Steve Suter's company. He wrote the book on performance. SpeedCurve is used for that. Server-side, there's 1,000 tools that you can use to measure server-side performance. But the thing I'm trying to get through in this slide is it's not just about measuring how long it took to render the page, right? If you're dealing with, entire countries of demand, you need to measure down to how long did it take to connect, how long did it take to make the DNS requests, how long did it take for the first byte to show up on the wire, how long did it take for the whole response to be returned. And all of these things you need to measure because you'll see this happen. From New Jersey, you might see the connect time spikes. And that might point to a problem with an ISP in New Jersey, right? The time to first byte might start to spike because there's a problem with a network switch that you wouldn't have noticed if you weren't watching that. All of these things contribute to user experience. And on that vein, you need to measure everything from everywhere. If you're just running a startup site, right, and you're deploying to Roku or something, you've got one server to hit. You may be fronted with a CDN. You've got really 2 points to measure. If you're running at scale, you've got a CDN. You need to understand the structure within that CDN. You get an edge server. You go to a regional server that the CDN runs. That goes to an origin host. That origin host might hit a number of different load balancers. Those load balancers might then flow into 3 or 4 services in between the CDN and your internal systems. What you need to do is you need to actually set up monitors that are running from different networks that hit each of those layers of the onion, so that if a problem exists, if a problem happens, you want to be able to, as quickly as possible, say, the problem is not this layer, it's this layer, but the problem is between this layer and this layer. So it's not enough just to say, is the site up? What part of the site is up? So, on failure, this is snake oil. People still sell it. The enemy of getting this right is guesswork. And I don't know if you've been at these companies. I've worked at these companies. It's not the company I work for now. But problem happens. You get a bunch of people in the room. And it's like, I think this might be because of the application servers. There's not enough of them. And you're like, this sort of gut feeling sense of diagnosing performance problems is pervasive. People just want to throw more capacity at problems all the time. And if NASA had thought like this, the rocket that they launched to the moon would have been like 1,000 stories high, right? You need to have a protocol for error analysis. And this isn't like the most fun thing in the world to talk about, right? That you need to have a series of Confluence pages that, that capture what happened. If I'm assuming all of you have a production site of some kind, right? When something goes wrong, how many people have a meeting to summarize, have like a post-incident summary meeting? Is that, yeah, so like a couple of you. Those post-incident summary meetings, nobody likes attending those, but they're the most valuable things in the world that you can do. Because you get people together in a room, you say, listen, nobody gets blamed or punished for this. We just want to find out what happened and how to avoid it in the future, right? You have a protocol for communicating this to management. And then I'm weird, so sometimes I listen to air traffic control for fun. And it's a very interesting thing. It's this structured way of communicating. So it's almost like a verbal TCP/IP, if you will. A controller says something to a plane, the plane has to acknowledge it, they have to deliver a message, the message has to be repeated. It really is like TCP. It really is like TCP. Every once in a while you'll hear a pilot, like during the Super Bowl, say, hey, do you have the score? And sometimes the controller will say, 25-3. Sometimes the controller will say, keep this channel focused, right? And that's when there's problems and you're dealing with failures and you're trying to diagnose systems, it's important to be able to say, let's keep it focused. Performance testing. So I'm showing this movie for a reason. Performance tests are fun. I'm going to say that, right? I want you to watch this closely. This is a test of the main shuttle engine in 1981, although it looks like it's older. At a certain point in this movie, and you'll see in a second, in which you'll see the engine changes state, right? And it's right here, it changes state. And see what it does? It wobbles, right? And it's because there are state changes in physical systems when you operate them under load, right? It's that wobble that you're looking for when you do a performance test, even on the website. If you don't do performance tests on websites, then you're going to end up with something like the Tacoma Narrows Bridge. Again, this is back to that book that I mentioned earlier. This is a bridge they built in Seattle, not sure exactly when, but they deployed their website to production without testing it, right? So essentially, that bridge underwent state change under performance load conditions that were not accounted for, were not tested appropriately. So when you run a performance test, when you take a system that's handling 10 transactions per second up to 1 million transactions per second, what you're looking for are those needs in response times. You're looking for the weak points. There's a famous hotel in Kansas City called the Hyatt. They suffered a failure of a walkway. This was in the 80s. And it was because one bolt was in the wrong place. Now again, we're not building walkways, bridges, or rockets. But if you do performance tests at scale, what you're looking for is the weak point in your architecture. So that's why you shouldn't just have a performance test where people show up and you get a dial up load and you have a party that works. The point of your performance test should be, are you testing the failure? Are you testing for capacity? But what is your SLA? Can you meet it? If you're operating under load, can you perform? Once you've specified your objectives, every performance test needs to have criteria for whether it worked or not. Again, it's really not about, hey, we're having a performance test on Wednesday night, everybody show up, get on the conference call, and see if it works. You've got to get scientific. You've got to have a working model for when it's going to fail. Don't start a performance test until you get somebody on the record saying, what do you think our capacity is? Do you want to test that? The goal is not does it work, the goal is how does it fail, when does it fail, what fails, what needs to be fixed. And that answer needs to be able to inform capacity planning. How many cores do you need? How many computers do you have running? What's the bandwidth that you require? And then the other goal, I think the most important goal of performance testing is getting people experience. Working under pressure to solve problems together, which is, again, something that I think the industry needs a lot of work on. Final warning about performance testing. The only real test of real traffic is real traffic. It's sort of like approaching an asymptote. You're not going to be able to recreate real user traffic. There's a certain amount of random magic that's present in a real user. Although that's maybe a little defeatist. Maybe someone will create product someday that will allow us to do it. That's why for your performance tests, or for your production deployments at scale, you want to consider A/B testing. And this is something that Marissa Meyer perfected at Google, which is take 1% of your customers, put them on the new system, and then measure the metrics after a day or after an hour, see if it works. Ramp deployments over time. Have 2 versions of the website, the old and the new, and dial it up slowly over a number of days. Shadowing is something that is interesting. I haven't done it yet, but that's taking, say, a service. Taking a service and using something like a network tab to send the same network traffic to the service that's not in rotation, right? Running it with real production traffic for a week and seeing if it works. It's not in the loop, but it's getting the same traffic. And then lastly, this performance testing. You need to have a group devoted to it. You need to have a way to measure it. But then the value is really the experience game. Getting your developers to participate in real performance tests so that they understand what to look for when the real traffic is flowing. So, performance testing antivirus, don't just show up and test and say, hey, it works. Checkbox. Instrument and measure everything that you're doing. Everything that you're doing. Don't wait until the performance test to think about the performance test. Like, try to get your developers to think about performance before. Understand single node limits, then averages. Very quickly, I hate averages. I lecture people about averages. It's a personality flaw of mine. But when somebody comes up to a performance test and they're like, everything's fine, the average response time is 100 milliseconds, I say, I paste this into a Slack channel and I say, we're not interested in that, we're interested in 95th percentile, we're interested in 98th percentile. If you're interested in averages, it means that you're fine with half of your customers having a valid experience, and the other half, who knows? It's an average. At scale, remember when I said it's the small things that will kill you at scale. If you have 1 million requests a second, which is a number I made up, it's not a real number. If the average is 100 milliseconds, but 10% of the requests are taking 2 seconds, that means you need to have 100,000 threads of capacity to handle those problematic requests. Right? It's about 95th. Don't measure averages during a performance test. The problems at scale are your queues are going to start to fill up. Then your Tomcat threads or whatever you use are going to start to be exhausted. And then at the highest level, the number of network connections to your data center. So decide what your sigma is, the standard deviations from the mean. If you're running a website for the local lemonade stand, maybe you're 1 sigma site. If you're selling something, maybe you're a 2 sigma site. If you're the kind of company that has ads on TV, you're a 3 or a 4 sigma site. So, single node performance. This is the first time I've used this Apple. Single node performance. This is where developers come into the mix. Early on in the process, you want developers to be comfortable with command line performance monitoring tools. I use AB. There's tools like AB and Siege. AB is built in to all the computers I'm using anyway on Linux and on Mac. Here's a really quick way to create 50 threads to hit the Yahoo site 20,000 times. And when you do that, what you're going to end up with is output that looks like this. It'll give you percentiles, right? Like 95th percentile for that request for 766 milliseconds. It'll give you connection time. Right? So I'm not saying this is the only performance tool that you should use, but you should get your developers in the habit of saying, I'm going to throw some load at my local machine, I'm going to see if it works. When you're doing that, you need to identify the breaking points. Is it CPU bound? Is it memory bound? Is it I/O? You need to make sure that your developers, most of them, understand how garbage collection works. This is a huge gap, I think, that we have in the industry. Anytime you ask somebody about the garbage collection, what you should do is you should have already Googled about the garbage collector. You should find out what the top 2 or 3 responses are. And if somebody comes back to you with the answer that's from one of those top 2 responses, tell them to go back. But don't make any assumptions. Every application is different. Java 8 has new garbage collection algorithms. Test them. Don't just tune your garbage collection because you found some page from 2010 that says these are the right settings to set. Characterize the heap in Java. Figure out how to run JStack. I think it's JMap. Figure out how to run those tools constantly. Initial testing, I'm a big fan of getting developers familiar with how to run these tools manually. I don't know if it really makes much sense from my perspective to automate it, because if you automate it, then it's like the developers aren't confronted with measuring this stuff from the command line. Single node performance, when you have 20,000 nodes, it doesn't seem like it's that important. But when something is going wrong, in the rare cases that something goes really wrong, you want to know that your developers can SSH to a machine and that they can diagnose what's going on a single node without having to rely on some automated system. So I'm a hippie. I believe that developers need to get involved with the hardware that their systems run on. So I have a holistic approach to DevOps. So who does all this? Developers. And that's key. Because if developers don't do this, then you create this culture that DevOps has been designed to fix. DevOps is supposed to fix the wall of confusion. Right? So with DevOps, you build it and you own it. Right? That's not totally true. Right? There are teams at scale. Developers can't build everything. They can't own everything. They can't own some of the complex network configuration that you need. Developers, for example, shouldn't know about the BGP protocol between your data centers. Right? So there are some limits. But developers at scale have new responsibilities. They have to build systems that have timeouts, use runtime config. They have to be involved in performance tests. That is not optional. They have to understand stuff like what's in front of the stuff that I'm publishing. The difference is between a car mechanic that's the inside of a 2013 Forester. It's a great engine. It does a lot of work. But this is the main engine of a shuttle. Right? So if you are a developer working at a system at scale, you understand that this is what you're building. This is not what you're building. They're two different skill sets. So this is a term I just made up. It's called scaled DevOps. Right? So DevOps is this. Let's just skip the next slide. This is our current concept of DevOps is nobody can tell me what to do. I'm a developer. Give me access. I'm just going to push it. And that's great. I actually like that. That's a great attitude. But in a scaled environment, there's so many people involved. You've got to learn how to communicate. It's more like this. And not the negative parts of this. Right? This is bureaucracy. This is a lot of obstacles. And if you look at the UN Security Council, this is sometimes a lot of conflict. But in a scaled DevOps environment, the people who succeed are the people who can communicate and who understand that there are different specialties involved. In a scaled DevOps environment, you have to talk to information security, network engineering, site operations, application platforms, logging and monitoring, problem management, production control, maybe a couple other groups in there. But you need to have either a group or a team that's able to take developers who are used to working in startups and bring them up to speed and adapt them to a scaled architecture. Right? You can still have developers who feel enabled to move quickly if you design your systems correctly. But at a certain level, you need to be able to have I would call it an education function internal to be able to bring somebody who's new to the org. These are the people you need to talk to. This is how the network works. This is how a NetScaler works. This is how Net5 works. These are the options that are available. When something goes wrong, these are the meetings that happen. These are the people in those meetings. These are the decisions that they're making. As developers, it's our challenge in a large enterprise to start getting a little bit more involved in operations. So, to me, scaled DevOps isn't as easy as the DevOps that I think we read about in the retail press. Scaled DevOps is like DevOps grown up. So it's your job to act as a universal translator. And again, I think scale is about people. It's not really about technology. Technology plays a part. It's about communicating. It's about capturing failure and guiding teams towards being ready to own production. Because not all developers are great at thinking about operations, right? But some really are. So it's your job, if you're responsible for DevOps at a place like this, to identify the resources who can sort of get into some of the operational responsibilities. It's about fostering relationships. It's not just about puppet, right? It's not just about can we run a show. And really everything is your responsibility. Because at the very end of the day, you are the one who understands how the application works, right? So you need to be involved with stuff like what's our routing look like, right? You may not really care about the details of regional ISP problems, but it's good to know about that. If you get a call from somebody asking you if there's a problem with the application, you can say, no, it's a regional ISP problem. If you don't find a way to get over that wall of confusion, it doesn't work. So DevOps is made of people. It's about getting developers on production. It's performance focused. It's sort of embracing failure. Like getting addicted to the concept that you want to get to 5 miles and what does it really mean to do that. So. And then finally, I can't emphasize this enough again. There are thousands, so I just gave a presentation, but there's really thousands of people responsible for what I was talking about. I mean, the number of people that this presentation covered, it's huge. And it really is, as developers, this is the kind of organization where you need to understand who you're working with. And there's just a huge list of people, and they're all really good. Really, if you think about a company, there's millions of people responsible. We have a great team, and if you're interested at all in working for Walmart, here's a website that you can go to, Walmart Careers. There's lots of opportunities. So that's it. That's my presentation.